Hi everybody, welcome back. In this video we're going to continue with the topic of classification, and in this notebook we're going to tackle multinomial classification, which involves classification of more than two classes. In order to introduce the topic, we're going to work through an example using a very popular data set which is known as the MNIST handwritten digit data set that contains thousands of grayscale images of handwritten digits 0 through 9. Before we dive into the details, let's just preview the topics that we're going to cover. We'll begin with the mathematical foundation that introduces a new activation function called softmax and also a new loss function, both of which are required for multinomial classification, which is also referred to as softmax regression. Then we're going to load the MNIST dataset, which is included within the TensorFlow distribution, which makes it really easy to access the data with a single line of code. After we split and normalize the dataset, we're then going to explain how the image data is processed through the network. This diagram actually looks much more complicated than it is, but we'll show you that it's very similar to the binary classification architecture that we reviewed in the previous video, with the main difference being that we now have 10 neurons instead of a single neuron. We're also going to spend a few minutes discussing what it means to have fully connected layers in a network, otherwise known as dense layers. And then we'll move on to the implementation in Keras, which is going to be very straightforward as we've shown before. We'll also explain how you can easily save and load models, which is very convenient. Then we're going to use the model that we've trained to make some predictions on the test data set. And as we showed in a previous video on binary classification, we'll show that we can produce a confusion matrix for all 10 classes as shown below. And then finally, we're going to end with kind of an interesting study of what the trained weights look like for 3 of the 10 output neurons when you reassemble the weights back into 2D images. As we'll see, each of these neurons has learned to detect the digit it was trained for. So let's go ahead and get started with the mathematical model for multinomial classification. First, recall that for binary classification, we developed a probabilistic interpretation for the output of the sigmoid activation function, which represented the probability that y equals 1 given x. And since we only had 2 classes, we were able to show that the probability of y equals 0 given x was just 1 minus y prime. So now we're going to generalize this concept to the problem of more than 2 classes. And as we'll see further below, when we have 3 or more classes, the network architecture will contain an output neuron for each class, whose output will be the predicted probability that the input x is associated with a particular class. And to do this, we're going to use a generalization of the sigmoid activation function called the softmax function to compute the probability that y equals a particular class given x. So assuming the number of possible classes is k, the following equation defines the softmax function, and the output for any particular neuron that has an input of z equals w transpose x plus b is defined by the following equation. Therefore, each output neuron I will compute a softmax score according to the above equation, and notice that the numerator is for a given class I, and the denominator normalizes the neuron's output. So the output of each neuron is in the range 0 to 1, and the summation of the scores for all neurons is 1. The output from each neuron, which is designated as y prime I, is interpreted as the probability that the input x is associated with class I. So now let's talk about a generalization of the binary cross-entropy loss function that applies to an arbitrary number of classes. Using the same motivation as we did with binary classification, we'd like to maximize the probability that y equals I given x, which we can transform to a minimization problem by minimizing the negative log of those probabilities. And this leads us then to the following loss function for multinomial classification, referred to as cross-entropy loss. In the notation below, we're making use of the indicator function in curly brackets, which evaluates to 1 when the expression inside the brackets is true, and evaluates to 0 otherwise. And in order to give you a better intuition for why this loss function makes sense, we've included a numerical example in the notebook description that you can study and confirm. So let's now continue on and load the MNIST dataset. We can do this with a single line of code as shown below using the load_data method. And that returns for us train and test data. We can then further split off a portion of the training data to be used for validation data as shown below. And notice that each data sample is a 28 by 28 2D array which contains the grayscale pixel intensities of each training image. Next, we're going to pre-process the input data by reshaping it from a 2D array into a 1D array. And we're also going to normalize the intensity values to the range 0 to 1. Notice that normalizing the data in this way needs to be done manually as shown below, since the normalization layer in Keras only performs standardization. As we mentioned in a previous video, normalization and standardization are both valid techniques that can be used to rescale data, and the choice often depends on the type of data you're working with. So in this case, we wanted to provide an example of normalizing the data to the range 0 to 1. So now we're finally ready to discuss this figure, and there's a few key points that we wanted to make. First of all, as noted above, we've flattened the input image data to be a one-dimensional array of length 784, where each of the elements represents the normalized grayscale image intensities. So in this example, the image intensities are going to be the features. Also keep in mind that it doesn't really matter how we flattened or unraveled this two-dimensional data as long as that processing step is consistently performed for all the data that's processed through the network. So next, let's focus on the fact that this is just a single layer network with 10 neurons, and the single layer is the output layer of the network. The connections between the input X and the output layer are fully connected, which means that every element in the input vector has a connection to every neuron in the output layer. As usual, the input into each neuron is the weighted sum of the inputs plus a bias term. So the input into the ith neuron is Wi transpose X plus Bi. Notice that the weight matrix W has a shape of 10 by 784. So each row in the weight matrix contains 784 weights that connect the input vector X to each of the I neurons. The output of each neuron is Yi prime, which is the predicted probability that the input is associated with the class for the given neuron. So for example, the first neuron produces the probability that the input was associated with class 0, which represents digit 0. In this example, it just so happens that the class index actually corresponds to the numeric value of the digit, but this not need be the case. So for example, if we were trying to classify images of fruit, then class 0 might be mapped to an apple and class 1 might be mapped to an orange and so forth. Finally, notice that the output of each neuron, Yi prime, is compared to the ground truth label Y so that a loss can be computed. Also notice that the name of the loss function that we're using here is called sparse cross-entropy loss because we're not one-hot encoding the class labels, but rather using labels 0 through 9. And then as we've shown before, the network weights can be updated using gradient descent and backpropagation. So that's a summary of the architecture they're going to be working with. It's actually very similar to the previous architecture that we used for binary classification, with the exception that we're now working with image data, which we're flattening into a 1D array, and we have an output layer that contains 10 neurons instead of 1 neuron. And finally, we're using a softmax activation function instead of a sigmoid activation function, and then a cross-entropy loss function instead of a binary cross-entropy function. Before we move on to the next section in which we're going to implement all of this in Keras, we just had a couple of detailed notes here in the notebook regarding the input feature transformations that we just described, and also a short discussion on fully connected layers, also known as dense layers, which we've been using in the last several examples, but we wanted to take a moment to formally define what that means. So as we mentioned above, a fully connected layer means that the preceding layer is connected to each of the neurons in the next layer. So we have two examples here in which we have a single input and 3 inputs. And these inputs, by the way, could represent network inputs or simply outputs from a previous layer in the network. In the first example, the fully connected layer has 7 weights because there's a connection from the single input to each of the neurons in the next layer. In the next example to the right, we're showing that we have 3 inputs, and so now each of these inputs is fully connected to each of the neurons in the next layer, which triples the number of connections, and therefore triples the number of weights from 7 to 21. So as you can imagine, when we start working with input images that have hundreds of pixels, and we start developing deep neural networks that have several fully connected hidden layers, we'll see that the number of parameters in a single architecture can easily reach millions of parameters. And so this starts to become an issue with regard to training runtime because of the sheer number of calculations that need to be performed, and also the amount of data that we actually need in order to train a network this large. So one of the topics that we're going to cover in the next module related to convolutional neural networks is the concept of pooling layers, which are intermediate layers within a network that downsize the data at various stages in the network in order to reduce the total number of parameters. So let's now continue on to the implementation in Keras. Since we've already covered this several times in previous videos, we're simply going to highlight the key differences between this network and previous networks. So first, notice that we don't have a normalization layer because we've already manually normalized our data further above. And then when we add the fully connected dense layer, we're specifying an input shape of 784 and 10 neurons for each of the 10 classes. Then when we compile the model, we're indicating sparse categorical cross-entropy as the loss function, and we're also specifying accuracy as a metric that we'd like to record, which will enable us to plot model accuracy further below. And then here we're training the model for 50 epochs with the training data, and also indicating the validation set so that we can plot both the training loss and the validation loss. And as you can see in the plots below, after about 10 epochs, the validation loss has completely flattened out, but the training loss continues to decline, which is an indication that we're starting to overfit the model on the training data. So we'll talk more about overfitting and techniques that can be used to mitigate this in future videos, but we just wanted to point this out if you're not already familiar with this topic. Notice that the classification accuracy is pretty good at 92% for the validation set, considering that we're only using the raw pixel intensities as features. But we'll see in future videos that when we start working with state-of-the-art convolutional neural networks, the data processing is much more sophisticated, and they can easily exceed 99% test accuracy on a data set like this. In this next section below, we're going to take a moment to describe a very useful feature in TensorFlow, which allows you to save your model to the file system and then load it back into memory, which is very convenient and something that you'll be doing quite a bit as you develop and train your own models. So in this case, we're going to save the model to the file system, which will create a folder structure on disk containing the model architecture definition and the weights of the network, among other things. And then here we're going to use the load model method to load it back into memory with a new name and continue on using it within the notebook. So it's the same model, we're simply demonstrating that you can load it in from the file system and continue using it. Next, we're going to take a closer look at using the model to make some predictions, and in the code below we're calling the predict method on the test data set and retrieving all the predictions for every sample in the test set. And then for the first test sample, which is index 0, we're printing out the ground truth label, which is 7, along with the predicted probabilities for each of the other classes. So as you can see in the output below, the predicted class is 7 because the 8th neuron, which corresponds to the digit 7, by far has the highest probability score. But it's also worth mentioning that if you look at some of the other numbers that could potentially be confused with a 7, for example, any digit that has a similar structure to a 7, like a 9 for example, it would make sense that the probability predicted for a class 9 digit might be quite a bit higher than some of the other digits that are structurally more different from a 7 or a 9. As we discussed in the video on binary classification, a confusion matrix is a very nice way to summarize classification results. And we can do the same thing here for all 10 classes by simply passing in the ground truth labels and the predicted labels to the confusion matrix function, and then use the heat map function in Seaborn to plot the results below. So there's a couple of things that are worth pointing out. First, notice that it appears that the digit 1 has the highest accuracy and digit 5 has the lowest accuracy. It's also interesting to note that when a 5 is misclassified, it's most often confused with either a 3 or an 8. As shown below, over 60 samples were misclassified as either a 3 or an 8, which makes sense since all 3 of those digits have a very similar line structure. One other thing we wanted to point out is that all these entries in the matrix represent absolute counts. So if the data set is somewhat imbalanced, then this format can be slightly misleading. For example, in the test data set, the number of 1s is quite a bit larger than the number of 5s, and therefore the total counts along the diagonal is not necessarily representative of the relative accuracy. So often a better way to view this data is to produce a normalized confusion matrix, which takes into account the number of samples in each class and produces a normalized value rather than an absolute count. So to do this, we're going to use a confusion matrix function from the scikit-learn library, which has an option to produce a normalized confusion matrix based on the ground truth data. As you can see below, the trend is similar but not quite as pronounced. So for example, 0 and 1 both have the highest accuracy at 98%. And now we can see that 3, 5, and 8 all have about the same accuracy, right around 88%, which makes sense since all three of these digits can sometimes get confused with each other. So both formats can be useful, and this is just something to keep in mind if you have a data set with imbalanced classes. In the last section of this notebook, we're going to take a look at what the trained weights look like for some of the neurons in the network. Since we're using the pixel intensities within each image's features, it would make sense that the weights have some intrinsic meaning for detecting the digit that they were trained for. So in the code below, we're retrieving the weights for digits 0, 1, and 2, and then we're reshaping them back into 2D arrays for visualization purposes so that we can compare them in a way that makes sense to us. Keep in mind that each of these images represents the weights associated with a specific neuron that's been trained to detect the associated digit. In the images below, you can start to see a high-level pattern emerging that seems to indicate a preference for a particular digit, and this is especially true for the digit 0 due to its symmetry and simple structure. The brighter pixels in each of these images represent larger weights, and recall that the pixel intensities in the input image get multiplied by these weights, giving rise to a numeric value that is added to a bias term and then converted to a probability through the softmax function. And therefore, an input image of a digit whose higher pixel intensities coincide with the larger weights in a particular neuron will result in a higher score for that particular class. So the brighter pixel intensities in an input image will activate regions of a neuron proportional to the weights in that neuron. This is easiest to see in the first example, which represents the digit 0. Notice that this roughly resembles the shape of a donut with a hole in the center. So the center region has lower weights, and then there's a circular region around the center that has much larger weights, which are displayed as brighter pixels. So the idea as to why this works is that the dot product between an input image of a 0 with this neuron would have the most chance to produce a higher score for this neuron compared to all other neurons. And as we saw in the confusion matrix above, the accuracy on the test data set is 98% when the input image is a 0, which is pretty impressive given the simplicity of this approach. So we hope that gives you some intuition for how this works. As we mentioned previously, in the next module, we're going to introduce convolutional neural networks, which have a much more sophisticated means for processing image data. As a preview, we've provided the following link below, which is a web-based animation application for several well-known CNN architectures. So to conclude this video, we're going to have a quick look at that. This is a really nice web-based application that you can experiment with to get a better feel for how CNNs process data. As we'll see in a minute, this is an interactive application that allows you to create or select input data and then drill down into various layers within a network. The network shown here is called LINET, which was the first example of a CNN architecture that was developed in 1998. We're going to cover CNNs in the next module, but we just wanted to give you a quick preview of what's to come. CNNs make use of several different types of layers, which typically include some kind of repeating pattern consisting of 2D convolutional layers with activation functions, pooling layers, and also normalization layers that are then followed by one or more fully connected layers that eventually lead to the final output of the network, which in this case is a softmax function for classification. So we're going to cover a lot of new terminology in the next couple of minutes, but don't worry about absorbing all this in detail. We simply wanted to introduce the topic and some of the nomenclature at a high level, and then in Module 3 coming up, we'll revisit all this material. So in order to demonstrate this, I'm going to draw the digit 7 in the right-hand panel. And once I do that, you can see that the network correctly predicts the input as a 7 as indicated below. And we now see that all the layers within the network have been populated with the data representation at each processing stage. So this makes a very nice visual way to walk through an example. So starting at the bottom of the page, the input that I just drew has been resized to a 28 by 28 grayscale image. This input layer is then padded with zeros along the border to conform with the expected input size for the Linnet architecture, which is 32 by 32, shown here in blue. And the next layer, shown in yellow, is a 2D convolutional layer that contains 6 separate filters, and this is why the layer is shown to have a depth visually. The filters themselves are smaller 5x5 patches that slide over the pixels in the input layer to produce an output. So when we expand this layer, we're looking at the output of the convolution operations from each of the 6 filters, and we refer to each of these outputs as activation maps. So we say that the depth of this layer is 6 because there are 6 filters and 6 corresponding activation maps produced. The computation performed between the filter and the input image is referred to as a convolution, which is why we refer to these layers as convolutional layers. And if you're wondering where the weights are in this network, they're associated with these 6 filters. So each 5x5 filter contains 25 weights, and since we have 6 filters, there's 150 weights, and then 1 bias term for each filter, which means that we have a total of 156 trainable parameters. And then the next layer, shown in blue, is a pooling layer that downsamples each of the activation maps to be 14 by 14 pixels. So this type of layer doesn't have any trainable parameters, as it's simply performing a downsizing operation. Then next we have another convolutional layer, shown in yellow, and this has a depth of 16, so it contains 16 5x5 filters, and the yellow slabs shown here are the activation maps produced by each of those 16 filters. And then next we have another pooling layer which further downsizes the activation maps to be 5x5 pixels. And then the last 2 layers shown in green are fully connected layers that connect the output of the last pooling layer to the output of the network, which is a softmax layer that contains 10 output neurons. And as you can see, the network is showing a 7 as the predicted value. So again, we covered quite a bit of material here, but this was just a high-level introduction to convolutional neural networks, which is the topic of the next module. So thanks so much, and we'll see you next time.